We've already introduced 5 logical connectives as a way to symbolize the logically important aspects of English sentences. We're now going to look at the truth tables for these connectives, which will tell us how the truth values of sentences that use them depend on the truth values of their parts. And we just have one straightforward aim in this lesson. Get familiar with the characteristic truth tables for our truth functional connectives. Remember that our focus in logic has been on declarative statements. Declarative sentences are ones that can be either true or false. And the significance of assigning a sentence a truth value is that the truth values of complex sentences can be built up using our logical connectives. Those depend on the truth values of their parts. So we can start by determining the truth values of atomic sentences. So if you have a complex sentence like Paris is in France or Tegucigalpa is in Nicaragua, that's made up of 2 atomic sentences. Paris is in France and Tegucigalpa is in Nicaragua. Well, the first one is true and the second one is false. So we assign truth values to those atomic statements that make up this complex sentence. Our goal now will be to go through each of the logical connectives and define for each one how the truth value of a sentence involving that connective depends on the truth values of the statements that make it up. So we're going to start with negation. And we're going to look at a written formal definition in a kind of logic-y English, and then look at truth tables. So a statement theta, that can be any logical statement. If we're trying to determine whether or not that's a logical negation, it will be just in case if the component statement alpha is true, then theta is false. And if the component statement alpha is false, then theta is true. That is a pretty abstract way of putting things, but we can capture it with a table. So take any sentence A. Remember that metalinguistic variables like A and soon B with this curly notation stand for any truth sentence of truth functional logic of any degree of complexity. So A can have 2 possible values. It can either be true or false. And what negation says is that if A is true, the negation of A is false. And if A is false, the negation of A is true. That's exactly what we got from that definition at the top. To illustrate this definition, let's look at 2 examples of negation sentences just to see that they satisfy that definition. So here's one negation sentence. Hot dogs are not sandwiches. That's true if it's false that hot dogs are sandwiches. So if our H is hot dogs are sandwiches, and that's true, then not H is false. Or if hot dogs are sandwiches is false, since this is controversial, then not H will be true. The same reasoning applies to treating the second example as negation. The game is unwinnable. That statement is true if it's false that the game is winnable. So we decide whether or not the game is winnable is true or false. And if it's true, not W is false. And if it's false, then not W is true. Let's now move on to conjunction. So take any statement theta. It's a logical conjunction just in case it's 2 component statements, the conjuncts alpha and beta. When they're true, theta has to be true. And if the whole statement is true, then the 2 conjuncts must each also be true. Again, we can capture that definition with the truth table. And here we need 4 rows to capture all the possible pairs of assignments of truth values to A and B. So if A is true and B is true, then the conjunction of A and B is true. That's what our first row tells us. The next 3 rows show that at least one of A or B is false. In the last one, both are false. Again, in the last 3 rows, as long as one conjunct is false, if you look at the final column, the whole conjunction is false. Again, let's look at a few examples. The conjunction terms in each of these familiar examples will have slightly different connotations, as we've seen, but in each case, the whole sentence is true if and only if the 2 conjoined simple sentences are true. So if our statement is, I like pets, but I hate having to clean up cat hair, that's true if it's true that I like pets and true that I hate having to clean up cat hair. Let's say it's true that I hate having to clean up hair, but it's false that I like pets. Then this whole thing is false, because we can't say I like pets, but I hate having to clean up hair if I don't even like pets. So in that case, the whole conjunction will be false because one conjunct is false. Again, in the next one, we have the word while as our conjunct word, and even though it suggests some contrast between the 2 statements, it still can be captured with our logical conjunction, because Gary's apartment is tidy while Vern's is a mess is true if it's true that Gary's apartment is tidy and true that Vern's apartment is a mess. So some of the meaning we normally take from words like but and while is lost by representing them as logical conjunction. But what's important is that we can represent the logical role these sentences play in inference and argument by symbolizing them using logical conjunction. A statement counts as a logical disjunction as long as it's the case that whenever one of the component statements, one of the disjuncts, is true, the whole statement is true. And if we consider the whole statement true, it must be the case that one or the other, or maybe both, of the component statements is true. So we can capture this table with the definition below in the table. And the important thing to notice is that the only time that a disjunction is false is when both disjuncts are false. So that's that last row. As long as one of either A or B is true, so that's the first 3 rows, the whole disjunction is true. But if both are false, the disjunction is false. Again, we'll look at a familiar example to see that that table makes sense. If our sentence is Jackie owns a black or dark gray car, this is true if Jackie owns a gray car. It's true if Jackie owns a black car. And it could also be true if Jackie owns both a black car and a dark gray car, which is exactly what our table reflects. The only way this sentence could turn out false is if Jackie didn't own a car in either of these colors. Let's say she only owns a red one. Then this sentence would be false. Now we're going to look at the material conditional. I want to flag that people find this one's characteristic truth table a bit more puzzling. I'll make some effort to motivate it, but you're also going to have to make an effort to just memorize it. Also, remember that the material conditional is directional, so you have to pay attention to which complex statement is the antecedent and which statement is the consequent. A statement counts as a material conditional when the truth of one component statement, alpha, the antecedent, is a condition for the truth of the other component statement, beta, the consequent. And we can formalize that by saying the statement is only false if the consequent is false when the antecedent is true. So that table below captures this definition. If the antecedent and consequent are both true, then the conditional is true. Let's look at the last 2 rows. If the antecedent is false and the consequent is true, the conditional is true. If the antecedent is false and the consequent is false, the conditional is still true. The only time a conditional is false is in that second row, when the antecedent is true and the conditional is false. We'll look at our boring familiar example to get familiar with why this truth table is fleshed out the way it is. So our example was, if it's raining, then I will bring an umbrella. And then we have R as our antecedent for it is raining, and U for our consequent, I will bring an umbrella. It's pretty natural to understand how we should treat the conditional when the antecedent is true. If it is raining, it makes sense to think that the whole sentence is true if I do bring an umbrella when it rains, and false if I don't bring an umbrella when it rains. So that captures that when the antecedent is true and the consequent is false, the conditional is false. We also have to consider the truth value of the whole conditional when the antecedent is false. So in this example, when it isn't raining, what should we say about the truth of the whole sentence? It seems wrong to say that the conditional is false if I bring an umbrella when it isn't raining. And it seems wrong to say that the conditional is false if I don't bring an umbrella when it isn't raining. Since it doesn't seem right to say that the conditional is false, no matter what we do, if it's not raining, if the antecedent is false, we assign the conditional true whenever the antecedent is false, regardless of the truth of the consequent. You might sense that the truth table for the logical material conditional doesn't match all of your intuitions for how we interpret if-then statements. And we'll see in the next video that there are some if-then statements that it just really can't explain at all. But for the most part, the material conditional is good enough to faithfully capture the role of most conditional statements in inferences and arguments. And again, that is our main concern. We'll wrap up by looking at the truth table for the biconditional. So a statement counts as a logical biconditional in the cases where if both component statements are true or both are false, the whole statement is true. Or when we think the whole statement is true, then the component statements ought to have the same truth value. So you'll see that in the first and last row, the whole biconditional is true. And that's because A and B, the component statements, have the same truth value. But the biconditional is false if A and B have differing truth values. So here's a kind of informal example of a biconditional. It's probably not something that we'd really say in a natural English conversation, but I think it illustrates the way the connective works pretty well. Robin talks to strangers on the street if and only if they're walking a dog. We can see that this sentence matches that truth table because it would be true if Robin talks to all strangers who walk dogs, and true if she doesn't talk to strangers who don't have dogs. But it would be false if she talks to some strangers who don't have dogs, or doesn't talk to some strangers with dogs. That's exactly what we were trying to capture. With the basic truth tables of each of these connectives under our belt, we'll be able to move on in the next one about how to use these truth tables to determine the truth values of more complex sentences that can be built up with these connectives.